Situation is this. Assume that we have two positive numbers, and if we have both L least common multiple and greatest common divisor L and G, then L is nothing but AB divided by G. So last time I showed that the uppercase L defined by this thing is a common multiple, right? Last time I showed this thing, and the next thing that I tried to show was the least number possible, right? The least number among all common multiples. So this part I tried, but I couldn't finish this part. So today I will finish. But if you have a question up to this point, ask me. Last time I completely showed everything up to this point, but I couldn't show. So this time, one more time, let's try. Assume that C is a common multiple of A and B. In other words, C is divided by A and then B. This means C is a common multiple of A and B. Then we can consider this C over L, and then C over L is nothing but C over AB over G, right? And we can rewrite it. It is CG over AB, and greatest common multiple can be written in terms of mathematical expression. How can you write this G in mathematical expression? How can you write GCD in mathematical expression using A and B? AX plus BY or anything, right? Last time I wrote down something I couldn't track down, but let's start fresh. So it is AX plus BY. Last time I wrote down something instead of XY, some letter, I was confused. But you may use any letter that you like, XY. All these numbers are integers. Then, if we divide this by A, then we get C over B times X. If we divide this by B, then we have C over A times Y. Straightforward calculation. Any questions? And take a look. C is a common multiple of B and A, right? C is divided by B, C is by A. So this is an integer, and this is also integer, right? So integer, and this is also integer. So integer times integer x plus integer. So all these are integers. So this is an integer. And all these things happen here because of this region. C should be some integer. C over L is some integer, and then C is integer times L. And as you can see, we are handling positive C, positive L. So positive number over positive number is positive. So this integer is positive. So we can say that it is greater than or equal to 1, right? Positive integer, right? Integer 1 multiplied by L. So we finished the proof, right? C is greater than or equal to L. Last time I was completely confused because I couldn't nail this part. And if you had the previous version, then you may write different letters instead of X, Y. But no big difference, right? X and Y are generic letters. In any case, we showed this completely, right? So I will review one more time. I showed last time that capital L is defined by this thing, and then L is a common multiple of A and B, right? Common multiple of A and B I showed last time. Do you follow me? Last time I showed it. And the only remaining thing that I didn't show was, I couldn't show was, whether it was the smallest or not. Do you follow me? And now I showed that it's the smallest. Why? Because C over L becomes an integer. And then, as you can see, C is positive, L is positive, so this integer is positive. So positive number all here, and then C is equal to integer times L, and a positive integer, that should be greater than or equal to 1. So C should be greater than or equal to L for any common multiple C, right? For any common multiple C. So this is not artificial one. For any common multiple of A and B, right? For any common multiple of A and B, we could prove this means L that we defined is lowercase l, right? Because of this reason, our uppercase L. So our uppercase L is the LCM, right? Least common multiple of A and B, or just L. And then we complete the proof. Because of this formula, we don't have to spend too much time on LCM. Why? If you need LCM, just AB divided by GCD. So proof is here, but the more important thing is this conversion. If you ask to handle LCM problem, all you need to do is handling AB over GCD problem. Any questions? Then next thing is, as I mentioned before, considering arithmetic progression with 4n plus even number, for instance 4n plus 0 or 4n plus 2, 4, 8, 6, these kind of things are all composite, right? We can extract 2. So only cases that we can consider is 4n plus 1 or 4n plus 3 case. But because it's tough, we only cover this case. But as I mentioned before, I will repeat it. Dirichlet showed this thing. For any GCD equal to 1 AB combination, for any GCD equal to AB combination, A something plus B set has infinitely many primes. In other words, if someone asks you whether there are infinitely many primes of this pattern, then the answer is yes. There are infinitely many primes of this pattern. What about this thing? GCD of 1 and 2 is 1, right? There are infinitely many primes of this pattern. Or this pattern, right? Or this pattern. There are infinitely many primes of this pattern when n varies from 0 to infinity, right? When n varies from 0 to infinity, for instance, 0 plus 2, 0 plus 1 plus 2, 2 plus 2, and so on. So 2, 3, 4, 5, 6. In this set, there are infinitely many primes. What about these odd numbers? 1, 3, 5, 7, and so on. And inside that set, we can have infinitely many primes, and so on. Or for instance, 1, 4, 7, 10, and so on has infinity. Do you follow me? So there are Dirichlet completely proved this case, but as I mentioned before, this requires some tools, especially called L functions. So instead of studying about L functions here, we will pick just one number for A and then one number for B. So we chose 4 and 3. And we will. Any questions? Then let's do it. First of all, before proving the big thing, we will prove small statement, small lemma. Assume that we have 4n plus 1 pattern in the set. Then if we multiply these kind of patterns, for instance, n1, 4n2, then what happens? We can multiply this through 16 n1, n2, and then 4 n1, and then this multiplication 4 n2, and then 1. Then you can extract the common factor 4, then 4 n1, n2, and then n1 plus n2 plus 1. And then we can write this thing using capital N and plus 1. So this lemma says, if we have 4n plus 1 pattern, the product of 4n plus 1 should give us 4n plus 1. It cannot give. What is the thing that you want to consider? These pairs cannot produce 4k plus 3 pattern, right? In other words, assume that we multiply 4n plus 1 pattern, so two pair, right? Well, a pair. So just one pair is good enough, but we can be generic. So we cannot produce 4k plus 3. Pick any two 4n plus 1 pattern. Like 5 and 9. 5 times 9 is 45, right? So it has remainder 1. In any case, this is very straightforward. Now using this, I will prove it. So as you have seen, proof by induction. Proof by induction, but you should know what we are proving. You should know what we are proving. The statement is this. There are infinitely many primes of this pattern, right? There are infinitely many primes of this pattern. So, proof by induction means we begin with what? Assume not, right? Assume not. Or, if we describe this clearly, and in the next column, I will describe this more clearly. Assume not means what? Assume that. So it's the same statement as the previous one. Assume that there are finitely many primes of the pattern 4n plus 3. So this is the assume not statement, right? To emphasize this finiteness, I will add there are only finitely many. In other words, we don't have infinitely many primes of this pattern. In other words, we negated the result. There are only finitely many primes of this pattern. Then let's write down all the possible numbers. Q1 of this pattern, right? Q2 of this pattern. And then there are only finitely many. So Q, let's use some, or like beta, right? Q beta. There are only finitely many prime numbers of this pattern. In other words, all other primes are different pattern than this one. I only collected this pattern. Do you follow me? So this is the key. Then what is it? Consider a number n which has 4 times all these numbers, q1 up to q beta. So I multiply all these numbers and 4 and then plus 3. So consider this number. Then what happens? What happens? This should not be prime. Why? Because if this is prime, then we violate our assumption. We said there are only finite many primes, say Q1 through Q beta. These are the all possible primes, right? But assume that this capital N is prime, then it violates our assumption. Do you follow me? So it cannot be. Means this should be, N should be divided by, N should have factors, right? By some numbers, right? Some numbers smaller than itself. Because if N itself is prime, then it's a violation of our condition, right? We assume that only there are Q1 through Q beta primes. But if this itself is also a prime, then already a violation or contradiction. So N should be this. Then we can break this down further and further and then get prime factors, right? So get some prime factors, say P1, P2, PR, right? We can break this down, right? It may repeat, right? P1 and P2 could be the same, but it doesn't matter. By fundamental theorem of arithmetic, we can break this up, right? We can break this up and then write in terms of prime factors. Then, can all these have, so my question is this, can all these be for N plus 1 pattern or not? Can all these be for N plus 1 pattern or not? If all these are for N plus 1 pattern, then 4N plus 1 multiplied 4N plus 1 pattern is also 4N plus 1, and it continues. Then it cannot be 4N plus 3 pattern. Right? It cannot be 4, and this is called N, right? 4N plus 3 pattern. Do you follow me? In other words, something here, some prime here, should be impossible, right? So I will write it. I will write the answer first. Impossible, right? In other words, there is some prime number, P, say, I used alpha, beta, gamma, right? P gamma, having this pattern, or something plus 3 pattern. If you don't agree with me, you can ask. So I'll pause and then you can check. So you should understand the strategy. We want to prove this by contradiction. Initially we said there are only finitely many primes, say Q1 through Q beta. And then we formed some number, but this number cannot be prime because of our strong assumption that there are only finite many, say these things, right? So it should be composite like this. Then by fundamental theorem of arithmetic, we can decompose it into prime factors. And then if all these factors have 4N plus 1 pattern, then end result will be also 4N plus 1 pattern. But as you can see, we begin with 4N plus 3 pattern. In other words, something should be 4N plus 3 pattern. Yes?
Do those two patterns, 4N plus 1 and 4N plus 3, does that cover all possible primes?
That's right.
Yeah.
Yes.
I thought so.
Any questions? And then, because of this reason, we have found PR pattern. Because of this region, we have found P gamma. And then P gamma is prime having this pattern, right? Having the pattern like this, right? Do you follow me or not? We decompose it. All these things cannot have, in other words, we cannot have this pattern all the time, because if you have this pattern all the time, the product will be the same pattern. So there should be something that doesn't have this pattern, in other words, the other pattern. So now we want to compare this P gamma and then Q1 through Q beta. So now we want to compare P gamma and Q1 through Q beta. So this is what I will do. Do you follow me? So let's check. Let's consider the, oh, sorry, it's meaningless. I made a mistake. So, to show that this doesn't belong to this finite set, I will consider the GCD, or division relation. So take a look. Q1. So the part is showing that I will write with red color. P gamma is not this one, not this one. So it doesn't belong to this one. This is the final portion to finish the proof, right? Do you follow me? This is the final portion to finish the proof. So how can you finish this thing? Q sub I from 1 through beta, right? Q sub I varying from 1 through beta, divides for Q1 for Q1 multiplied by Q2 all the way through Q beta. Do you follow me? Because some Qi exists here, right? So automatically divides. In other words, Q sub I divides n minus 3. I will go to the next page, but if you have a question, ask it. So let's do it. P sub gamma divides n and Q sub I divides n minus 3 for all I varying from 1 through beta. So this statement we could obtain. So now I will define M. I will define M, which is given by this statement, 4 times Q1 through Q beta minus 1. Now you will clearly see the reason, because if you take minus 1 here, then what happens? 4 Q1 Q beta will become M plus 1. So we can completely replace this by M plus 1, right? I initially started with plus 3, and then 3 caused some problem, so I replaced the number n by capital lowercase m plus 1. So we can I really dislike the situation, because what he did was, with 3, so I will fix this quickly. This way, we can completely fix the problem. In other words, when I initially used capital N, I felt that's enough to nail it, but in the end, I found the 3 is bothering us, so I will redescribe the situation using lowercase n instead of capital M. But as you can see, everything is the same as capital N. Take a look. 4 multiply these numbers by this one. And is there any change? Essentially the same, right? Then by the same reasoning, we can find P instead of gamma. We can use, what else? Alpha. Alpha we didn't use, right? We can find P alpha dividing M, right? Having pattern 4n plus 3. 4n plus 3. And as you can see, now we arrive at this situation. P alpha has this pattern, and then divides M, and then the previous statement, like this, right? Like this. Qi divides M plus 1. So do you now sense what I am going, where I am going, right? Qi dividing M plus 1. Do you see it? So we are almost there, right? If you completely follow me, ask. If you don't completely follow me, ask. So we are now adjusting the number 3. So to remove this 3 factor and then create 1, I subtract 1. Do you follow me? I subtract 1 instead of adding 3. Take a look. I subtract 1 here instead of adding 3. So we essentially get the same result. And we are here. If you don't agree with me, you can ask it. Then let's finish it. Because P alpha divides M, Q divides M plus 1, P, Q, just a moment, P alpha, so what can you say? Anything is possible, but what can you say? Right here, we worked hard to arrive at this point, and then we should get a conclusion. QI, let's go back. So currently we are here, and I'm checking what we need to do. So this is thing. Now I get it. Assume that P alpha happen to be some QI, right? I is generic. Assume that P alpha belongs to that set. Then what happens? These two numbers are the same, right? These two numbers are the same. Then it means QI divides both M and M plus 1. Do you follow me? If this number belongs to the set, then it should be the same as some QI. To be more specific, we can say QI not or QI1 or this kind of thing is not necessary, but you can add to distinguish it from generic one, right? So P alpha happen to be some Q sub I sub 1. Then what can you say? If some number divides A and B, then it divides A plus B, A minus B, any possible combination, right? Because A divides both numbers, then we can say QI divides this number minus this number, or QI divides 1. Is it possible? Is it possible? It's impossible, right? This is not possible. QI has what pattern? QI has 4 something plus 3 pattern, right? Right? QI has this pattern in the first place when you defined. So now, because of this, a contradiction, right? So, this is the end of the story, right? Because of this, I will write a few more lines. So I completely showed you why it cannot happen by contradiction. So we assume that there are only Q sub I, right? Q sub I are all possible primes of this pattern. And then I created P alpha having the same pattern. Then this P alpha should be these things, right? Should be these things, because there are only finite many. But as you can see, P alpha, if P alpha and QI are equal, then it divides both numbers, right? Both numbers. That means it divides 1. In other words, this divides 1. Is it possible? It's impossible, right? So I will pause and then wait, and then you can check whether you completely follow this idea or not. So initially I tried with 3, then we will have 3 in the end, right? We will have 3 in the end. Do you see it? If P is 3, then we will have 3 here in the end. Then there is a slight chance having prime, right? Do you follow me? This is the reason why I adjusted the number a little bit to create this kind of thing, right? So instead of just having these product plus 3, I subtracted 1 and then 3, and I followed all the same steps. Do you see? So proofs are not made correctly in the first place. People try and find some problem, then fix it, and then retry, and then we arrive at the result. So you saw it, right? So you should know the situation. Sometimes someone memorize all the formula and steps and come and teach you. I really do not like it, because if I do that, then when you see me doing it, you know you are knowing. You think you are knowing, right? You know those things because it was flawless, right? But you don't learn, because when you really want to prove, all sorts of strange things happen, then you don't know what is wrong with you, because when I saw instructor doing it, I saw it. But when I try to do it, I cannot. But if I do not memorize and then try to lead to a solution and fail, then you see what kind of thing caused the problem. What was the reason you cannot go to the result, then you can learn, right? So as you can see, initially I tried this with 3. And then as you can see, if I leave 3 alone, then I will have m and m plus 3. Then I will have the result like qi divide 3. Then here it's not very difficult to finish the statement, right? Because I have 3. So I sense that we need to adjust a little bit in this place. So after knowing this fact right here, right, I decide to adjust it. How? I subtract 1, right? So some of you may wonder why this subtraction is necessary. But as you can see, if we use plus 3, we arrive at qi divide 3 situation, right? Qi divides 3 situation. But because of this adjustment, now this becomes m, right? This becomes qi divide 1 situation because m and m plus 1. So do you clearly see the slight adjustment proving the result? Without this slight adjustment, you cannot prove it. But with this slight adjustment, it was. I will pause so that you can see all these things and effort. But initially, with my effort, I arrive at some inconclusive situation having n and n minus 3. So to nail it, I didn't use this pattern. So I adjust how? I subtract 1 in this inner part, meaning plus 3 becomes negative 1, right? Then because of this reason, we can arrive at this point. So then you clearly see why we should begin with this number instead of plus 3. Do you follow me? So this is it. The next one is the final proof related to primes. And afterwards, I will answer questions. And before answering questions, I will summarize for the exam. So let's do it. The last statement that I want to prove is this thing. Assume that we consider arithmetic progression. For instance, P and then P plus D, and then P plus D, or P plus 2 times D, right? And then P plus 3 times D, and then P plus N minus 1 times D. So how many numbers are there here? How many numbers can you find here? Total n numbers, right? 0D, 1D, up to n minus 1D. So total n numbers. So there are n numbers inside this arithmetic progression. So this is the assumption. Assume that all these are primes. So we assume that all these things are prime. So all these are prime numbers. So all of these are. Then what is the? So assume that is a little bit. Assume that is used for a little bit different purpose. So I will say just if, right? If might be enough, because assume that is used for the contradiction proof part, right? So if are all prime, then D is divided by all prime numbers or previous prime numbers. Or previous prime numbers. Less than n. So I might need to describe it instead of mathematical expression. I will just describe it using the sentences. So I will just say, then D is divided by every prime less than this number n. If you see the proof, you will understand the situation. So you may find any arithmetic progression having this pattern. So what do you want? For instance, 3, 5, and then 7. Then how many numbers can you find? How many numbers can you find in this arithmetic progression? How many numbers can you find? 3 numbers you can find, right? Then P is what? If you use letters, P is what? P is 3. D is what? And then there are 3 numbers, right? So let's check this statement. This D, this 2 is divided by every prime less than 3. What is it? 2, right? 2 divides 2. Done, right? Can you find different arithmetic progression than this thing? Can you find any arithmetic progression? We should increment by even numbers, right? 3, 7, 11 is not an arithmetic progression. We increase the same amount each time. So 7, 9, 11 is arithmetic progression, but 7, 11.
I mean, skip 5.
3, 7. Right. Thank you. Then, what is P? P is 3. D is what? 4. N is 3, right? Then, this D4 is divided by the prime number smaller than this, that is 2, right? Every prime number smaller than anything having bigger gaps. Like I want to use 10. Can you find something? 23 already. What is it? Great. Thank you. So, in this case, P is 3. And D is what? Each time, the increment is what? 10, right? And how many numbers can you find? Total 3 numbers. So, every number less than this is 2, right? Every prime that is less than this is 2, so 2 divides 10. Can you find longer progression than just 3? I used enough 3. I want to use longer progression. The text might have it, so let's try to find something. So here it is. Very tough to find these kind of things, but they found one. 22 2, 5, 1, and then increment of 6, 2, 5, 7, increment of 6, 2, 6, 3, increment of 6, 2, 6, 9, all primes. So we have 4. At least we can now guess. P equals what? 251. D equals what? 6. And then how many numbers? 4 numbers involved. So what are the primes less than 4? 2 and 3. Does this number, do these numbers divide 6? Right? So it looks strange, so I will rewrite it. So as you can see, this statement is true, but as you can see, the difficult part is not really showing this thing. Finding this kind of progression is tough. As I mentioned before, give me any big number, I can find consecutive composite numbers. But finding consecutive arithmetic progression producing prime is very tough, as you can see. In any case, we have shown enough. We have seen enough, right? So let's prove it. Assume that, so what? Proof by contradiction, right? Proof by contradiction. So assume not. So what is the actual statement of assume not? What is the actual statement of assume not? It is this. Assume that there is some prime. There is a prime number, or prime can be used as noun. Say P, which does not divide. Divide is used by bar. So if we just strike this, then it is does not divide, right? Does not divide D. Do you follow me? Of course, all these are less than n, right? All these numbers are less than. So assume that there is a prime number which does not divide D, which is less than n. Then we can say this. Then we want to go to contradiction. Consider the progression. Consider the progression like this. Oh, sorry for this usage because I used P in the first place. Do you follow me? When I described the theorem, I used P. I used P here, right? So I will adjust it. So what do you like? Do you want to change this completely or use some subscript? So let's use Q because there could be possible confusion. So let's use Q. Because if I use P, then you might be confused, right? So I will use Q. So consider the arithmetic progression of Q numbers. So total Q numbers will be considered. Q numbers will be considered. Then P plus D, P plus 2D, 3D, 4D, 5D, and so on, right? And then, and in the end, Q minus 1D. Then, claim. This is my claim. My claim says if we divide by Q, if we divide those numbers, if we divide these numbers by Q, then the remainder will be 0, 1 up to q minus 1 by division algorithm. So this is the claim that I want to prove. So there are total q numbers. If we divide these q numbers by q, then the remainder could be 0, 1, 2, up to q minus 1. This is the claim. Then, after proving this claim, what can you say? We can say that some number here has remainder 0 if we divide by q. In other words, some number here is divided by q. That means it's not a prime. In other words, contradiction. Because in the first place, we said big if. If all these are primes, right? Do you follow me? You should know where we are going. So we should know the goal, and then we should arrive at the destination by adjusting and then resteering and so on, right? So we are doing it. So once I prove this thing, I will end the proof by saying that the remainder 0 means this some number here is divided by q. That q is less than this number, right? N. And then that will end the proof, right? That will end the proof. So very many things. As I mentioned before, this course is extremely tough, not because of calculation, but because the requirement of proofs, right? Then let's go to the next page. So for this claim, I also claim proved by contradiction. To prove just the claim, I use this contradiction idea. In other words, q numbers, total q numbers, divided by q. So by contradiction, assume not, right? Assume not for the claim means q numbers, total, we have q numbers, right? Q integers divided by q have a pair sharing the same remainder. Do you follow me? I said when you divide q numbers by q, then the remainder will be evenly distributed, right? Evenly distributed between the numbers, right? Between 0 to n minus 1, 0 to q minus 1. So I want to prove this statement, right? Evenly, assume not. In other words, it's not evenly distributed. That means some remainder might be missing. Some remainder might be shared by other number. Do you follow me? In other words, if this happens, then among these possible numbers, p plus d, p plus 2d, and so on, p plus id, I am adding a few more things, and then p plus jd, and then in the end, p plus total q minus 1d, and then how many numbers can you count? The total. So among these q numbers, some numbers may share the same remainder. some number may share the same remainder. Right? In other words, P plus JD and then I minus P plus ID share the same remainder, then remainder is gone because of the subtraction. Do you follow me? Because they share the same remainder and the remainder is gone. Then, because the remainder is gone, it will be divided by Q. Do you follow me? Or not? So it's long, right? In any case, P and P are cancelled out. And then we have a common factor, J minus I, D, and then Q. But by the assumption, Q does not divide D. Do you follow me or not? By the assumption, in the first place when Q was chosen, Q it does not divide D in the first place. Because Q does not divide D, and the Q is prime, by Euclid lemma that I proved, either of the two should be divided by prime. Because it's prime, it happens, right? Because Q does, because of these two facts, Q divides J minus I. In other words, J minus I is divided by Q, meaning J minus I is either 0 or bigger or equal than, right, greater than or equal to Q. Do you follow me? But in the first place, I said, assume not. In other words, I and J are different in the first place when I assumed this, right? Do you follow me? Assume not that I and J are different. So it cannot be 0, meaning J minus I should be multiple of Q. But these numbers I and J are between 0 and Q minus 1. Then can this difference be greater than Q minus 1? Impossible. So contradiction. So contradiction to claim, right? So this proves the claim. Right? This proves the claim. Because I proved the claim, I can now use this to finish it. So I will go to the next column and then finish the proof of the theorem itself, not this small statement. Then let's go to the next column. Then some number P plus some number D has remainder 0, meaning Q multiplied by some number, and then remainder is 0. And then as you can see, Q is not greater than those things. So what does this say? It says P plus this number D is not prime. Contradiction. So we finished the proof. So proof by contradiction is this. We claim that the result is not true. In other words, assume not. And then we lead to a contradiction. And then we prove the claim. So I will pause, and then you can check and then ask questions. Because in the first place I said all these things are primes, right? P plus something D is prime. But as you can see, it's not the case. Then I don't want to prove any more today. I want to describe many things, but I don't want to prove any more. So let's summarize. In chapter 1, we learned about induction, right? Mathematical induction. And I mentioned about discourse version induction, right? Discourse version induction. But if you are interested, then you can read the book to find 2 cases given by the problem. Discourse induction said this. The statement is true for any integer, right? Any integer. So say, for instance, 5, right? And then you say, if it is true for k, then it is true for k plus 1. So if you prove first step and then second step, then induction is done, right? This is the discourse version induction. Then what is the difference between discourse version induction and 2 inductions in the book? Essentially the same. Essentially, the book fixed this number to 1, right? The book fixed this number to 1 instead of any number. Then what can you do? We can just increase the number or decrease the number to accommodate, right? And the second thing is, second induction is, assume for every number up to n minus 1. Then, and in other words, essentially the same, right? Essentially the same, but every number. Then, what has more assumption? This one or this one? It sounds like having more assumption. Assume that it is true all the way up to n minus 1. Then it is true for n. It's the second induction. Do you get it? In this case, we have only one assumption, and then with one assumption we can get the next. But second induction has more conditions, right? And then with these many conditions, we lead to the result. So essentially the same. So as I mentioned before, I mentioned about this course version, then you will get the full credit. But if you want to learn about first or second induction in the book, you can read those things on your own. The next thing is, I will just browse the book and then mention about the things that we covered. So with the induction, you can prove many things. And the next thing is division algorithm. Division algorithm is extremely important. Why? Because if you are asked to prove something, then mostly, for instance, prove that something is divided by 5. Then generally, to prove this kind of statement, all you need to do is dividing generic number n by 5. So if you divide generic number by 5, then there is quotient and the remainder. Remainder could be 0, 1, 2, 3, 4, right? These are possible remainders, right? These are possible remainders. So this is called the division algorithm used in proofs. When you are asked to prove that something is divided by 5, then you divide generic number n by 5, and then use this thing, and then you should prove all 5 cases. Prove this case, 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 right? All 5 cases. If you need an example, ask me. For instance, for any prime, I will state one example using this idea. For any prime p plus 2, p plus 4, right? Arithmetic progression by the difference 2, right? We have p, and then 2, and then 2. This is the claim. One of this number is divided by, at least one of this is divided by 3. One of this is divided by 3. Then how can you prove it? Divide by 3. I said divide by 3. Then what should you do? Assume that, first of all, p divided by 3, right? P divided by 3, then the quotient and then remainders are what? 0, 1, 2, right? So assume that p equals, it's impossible, right? Because it's prime, this is impossible. This is impossible. Oh, k, when k is equal to 1 is possible. So 3k or 3 is the same thing, right? 3k or 3. Because 3 is alpha, which k equal to 1 is. Assume that P has this pattern, then already 3k plus 2, 3k plus 4, and then this number is divided by 3. So I proved one case. Do you follow me? Then, first assumption, so we need 3 assumptions. Assume that P is equal to 3k plus 1. Then what can you say? First number is 3k plus 1. Second number is 3k plus 1 plus 2. Third number is 3k plus 1 plus 4. Then as you can see, this number is divided by 3. Finally, assume that P is 3k plus 2, then 3k plus 2, 3k plus 2 plus 2, 3k plus 2 plus 4. Do you get it? This number is divided by 3. So you finish the proof. Division algorithm is a very, very powerful tool that you can use when you ask to prove something is divided by something, right? Right? Some statement is, some term is divided by a fixed number. Then, instead of dividing the whole thing by a number, you divide generic numbers such as P or N by the given number, and then use the division algorithm. Do you get it? Then the more important thing is technical usage of these things. When we divide a number A by B, then there is quotient and the remainder. So this is the equality representation. And in elementary school, you learned about long division. A is divided by B, then quotient is B, and then you can multiply B and Q and then subtract, and then this becomes R, right? So you learned about it. But as I mentioned before, these are difficult to stack. This is possible to stack, but if we stack, we need to write down equal symbol, and then these numbers and plus sign and so on. So because of this reason, we stack this way. A divided by B. Then quotient is Q, and the remainder is R. So we use this, then we can stack, and then repeat. So this was learned. Then very important statement is this. Under this condition, GCD of AB equals GCD of DR. Very important. This enables Euclidean algorithm. In other words, big number divided by small number, then you don't have to worry about big number. You need to worry about small number and then smaller number. Do you get it? So big number, small number becomes small number, smaller number. So when you have A and B, then you should worry about B and R. So Euclidean algorithm is enabled, and then this kind of stacking is possible. Then the next thing is really doing Euclidean algorithm, then just A, B, and so on. So say assume that we have 24 and then 16, then we can find the quotient 1, and then if we multiply then subtract, then it is 8. Then if we divide this by 8, then quotient is 2. If we multiply this and subtract, you get 0. So the number above this 0 is the GCD, right? So this is the GCD. So we can find the GCD by Euclidean algorithm extremely fast, very, very efficient, and this enables the encryption, and your cell phone has this routine embedded. Then, instead of just using it for the GCD evaluation or calculation, we can use some simple idea using equality, right? So take a look. We have 24 equals 24 times 1 plus the other number, 16 times 0, or 24 times 0 plus 16 times 1. then we can add equality, we can multiply any number to a certain equality, we can subtract, all sorts of things are possible, right? So we do the same thing that we did to this term, or this term, to create this one, and then we can apply the same thing to this number and this number. So because of this reason, what did we do? We multiply this number by 1, so I multiply by 1 and then subtract, right? So we do the same thing. We multiply this number by 1 and then subtract, right? We multiply this number by 1 and then subtract. And then all others are just attached here. So we can continue these kind of steps. But as you can see, if we stack this way, then equals symbol plus and many numbers. So instead of writing down all the details, we skip and then just extract the necessary part. 24, 16 given by the problem, and general Euclidean algorithm. And then after writing general Euclidean algorithm, we can just stack 1, 0, 0, 1, and then we do the same thing that we did to this number and this set, right? This pair. And then we get 1, and then we get negative 1. Then we have found these numbers, and then these are the solution to the Diophantine equation. 24, say x plus 16 times y equals 8. So Diophantine equation can be solved by this simple idea. As I mentioned before, on the exam, you can use any method of your choice. Any method. You don't have to rely on this method. In any case, we can solve the Diophantine equation. But is this the only solution? In other words, I solved this thing. 24x plus 16y equals 8. I solved it. But can you find all the solutions? Well, sometimes solution may not exist. For instance, assume that the right side 1. The solution doesn't exist, right? So I don't want to review the bad case. I want to, we don't have enough time. So let's stop here. And the next time, we'll continue these things.